right now, tonight. While you lie there listening to this, the moon is moving away from you. Not falling. Not drifting off into some dramatic, sudden escape. It is doing something far quieter and far stranger. Every single year, the moon moves about 3.8 centimeters farther from Earth, roughly the width of 2 fingers pressed together. That is all. A distance so small you could not measure it with your own eyes across an entire human lifetime. And yet it is happening, continuously, silently, with the reliability of a clock. And it has been happening for billions of years. And it will keep happening for billions more. It sounds like a small fact. 3.8 centimeters a year barely registers as movement at all. But small, patient processes, given enough time, become enormous. 3.8 centimeters a year, multiplied across 4.5 billion years, means the moon we see tonight, the moon that has hung in Earth's sky since before there was anything alive to look up at it, used to sit dramatically, almost unrecognizably, closer to Earth than it does now, multiplied forward into the deep future. That same slow drift means the moon we know is not a fixed, permanent fixture of our sky. It is a guest, slowly, quietly, letting itself out. Tonight, we're going to follow that story in both directions, backward, into the moon's violent, fiery birth, when it may have hung so close overhead that it filled a significant part of the sky, and forward, into a future far beyond anything you or I, or any human being will ever witness directly, toward a distant point where Earth and its moon settle, at last, into a strange, locked, permanent relationship. And what that means, quietly and specifically, for the length of your days, the tilt of the seasons, and the stability of the very climate that allows anything on this planet to exist at all. You don't need to hold on to the numbers. Let them wash past you if they need to. This is a story told on a timescale so much larger than a human life that there is nothing here to worry about. Nothing here to fix. Nothing here that requires you to do anything at all except listen and drift. While one very old, very patient story continues to unfold exactly as it always has. Let's start where it began, with a collision. The violent birth of the moon. The leading scientific explanation for how the moon formed is known as the giant impact hypothesis, and it describes an event so violent that, if you try to picture it fully, it stops feeling like ordinary planetary history and starts to feel more like the origin of myth. Roughly 4.5 billion years ago, not long after Earth itself had formed and begun to settle into a molten, differentiating ball of rock and metal, a Mars-sized protoplanet, a world roughly half the diameter of Earth, given the informal name Theia by planetary scientists after the Greek Titan who, in mythology, was the mother of the moon goddess Selene, collided with the young Earth at a glancing angle, at extraordinary speed. The collision did not simply crack or dent early Earth. It very likely liquefied a substantial portion of both bodies, throwing an immense plume of vaporized and molten rock into orbit around the newly reshaped Earth. Over a relatively short span of time afterward, some simulations suggest as little as a few decades to a few centuries, an almost unbelievably fast time frame on a geological scale. That orbiting debris field began to gravitationally clump together, accreting into a single, mostly molten sphere, the moon. This origin story is supported by several independent lines of evidence that, together, make it the dominant model among planetary scientists today. Lunar rock samples brought back by the Apollo missions show striking chemical similarities to Earth's mantle, particularly in the ratios of certain oxygen isotopes, suggesting the moon is built substantially from material that was once part of Earth itself, or from a colliding body with an almost identical isotopic fingerprint. At the same time, the moon is notably depleted in volatile elements and water compared to Earth, consistent with a formation process involving intense heat and vaporization. Exactly the kind of violent, high-energy event a giant impact would produce. And the moon has a surprisingly small iron core relative to its size compared to Earth, consistent with the idea that it formed primarily from the outer rocky material of the colliding bodies, rather than incorporating much of either object's dense metallic core, which would have preferentially remained with Earth. Whatever the precise details, the outcome of that collision was a newly formed moon sitting astonishingly close to Earth. Current estimates suggest an initial distance of perhaps 30,000 kilometers, compared to the roughly 384,000 kilometers separating Earth and the moon today. That means the early moon may have orbited at somewhere between 1/20th and 1/10th of its current distance. Picture what that would have meant, standing on Earth's surface in that unimaginably distant past, if there had been anyone there to stand at all. The moon, that close, would not have been the modest, comfortable disk we glance at tonight. It would have dominated the sky, appearing many times larger than the moon does now, close enough that its surface features, its craters and dark plains, would have been visible without any instrument at all, simply as texture on an enormous, looming presence overhead. And it would have moved fast. Moon, that close orbits far more quickly than one at greater distance, meaning Earth's earliest days and nights cycled at a pace almost impossible to picture from where we are now. Some estimates suggest Earth's very first days, shortly after the moon's formation, may have lasted only about 6 hours, spinning far faster on its axis than it does today, with the moon racing across that vast, close sky in a matter of just a few hours per orbit as well. That combination, a young Earth spinning rapidly and a moon sitting close and heavy in the sky, set the stage for the very process that has been slowly separating the two of them, patiently, continuously, ever since the tides. How we actually know the moon, I know, is moving away. It's worth pausing here before going further to explain something that tends to surprise people the first time they hear it. We don't just suspect the moon is receding from Earth. We measure it directly, continuously, with a precision that would have sounded like science fiction only a few decades ago. The story of that measurement begins with the Apollo missions. Between 1969 and 1972, astronauts on the Apollo 11, 14, and 15 missions placed small devices on the lunar surface called retroreflectors, arrays of specially cut mirrors, similar in principle to the reflective panels on a bicycle pedal or a road sign, designed to reflect light directly back toward its source, no matter the angle it arrives from. Soviet Union's uncrewed lunar rovers placed similar reflectors on the moon around the same period. These devices have no batteries, no moving parts, and no power source at all. They don't need one. Their entire function is passive. Sit on the lunar surface and wait to be hit by a beam of light from Earth. And that is exactly what observatories on Earth have been doing, essentially without interruption, for over 50 years, in a technique called lunar laser ranging. Powerful lasers fired from observatories, such as the Apache Point Observatory in New Mexico, are aimed with extraordinary precision at these small reflectors on the moon's surface, roughly 384,000 kilometers away. The beam spreads out over that distance, arriving at the moon as a spot several kilometers wide, and only a small fraction of the photons in that beam actually strike the reflector and bounce back toward Earth. of the light that does return. An observatory might detect only a handful of individual photons per pulse. But that is enough. By measuring the precise round-trip travel time of that light traveling at exactly 299,792.458 kilometers per second, a physical constant known to extraordinary precision, scientists can calculate the Earth-Moon distance at the moment of that specific pulse to an accuracy of just a few millimeters, across a distance of hundreds of thousands of kilometers. Repeating that measurement night after night, year after year, across 5 decades now, has produced one of the longest-running, most precise datasets in all of experimental science. And the trend it reveals is remarkably clean and consistent. The Moon is receding from Earth at a rate of approximately 3.82 centimeters per year, a figure now considered one of the best measured quantities in all of planetary astronomy, refined and cross-checked continuously across half a century of nightly laser pulse, as bouncing off mirrors left behind by astronauts who, at the time, were focused on entirely different scientific goals. There is something quietly moving in that, if you sit with it. A handful of small mirrored panels, placed by human hands on another world more than 50 years ago, sitting silently in lunar dust the entire time, doing nothing at all, and waiting. And in that waiting, becoming one of the most valuable scientific instruments human beings have ever built, simply by existing in the right place, prepared to answer a question that, at the time they were placed, most people hadn't even thought to ask. Before lunar laser ranging existed, scientists had other, cruder ways of suspecting the Moon's recession, some of which reach much further back into history than you might expect. Ancient astronomical records, Babylonian eclipse observations, ancient Chinese and Greek records of the timing and appearance of solar and lunar eclipses, stretching back over 2,000 years, have been used by modern researchers to reconstruct subtle, long-term changes in the Earth-Moon system, because the exact timing and visibility of an eclipse from a given location on Earth depends sensitively on the Earth-Moon distance and on the length of Earth day at the time. By comparing where and when ancient eclipses were actually recorded as visible against where modern orbital mechanics would predict them to have been visible if nothing had changed, astronomers have been able to detect the fingerprints of a slowly lengthening day and a slowly receding moon, embedded quietly in observations made by people who had no concept of tidal physics, writing down what they saw simply because eclipses seemed important enough to record. Geology offers a third, even deeper line of evidence. Certain sedimentary rock formations, particularly ancient tidal rhythmites, layers of sediment deposited in tidal environments where each layer corresponds to a single tidal cycle, preserve a kind of natural calendar. By carefully counting and measuring the thickness of these layers in rock formations hundreds of millions of years old, geologists have been able to estimate how many days made up a year and how long each day lasted deep in Earth's geological past. A particularly well-studied set of formations, roughly 620 million years old, suggests that Earth's day at that time lasted only about 21 hours, with a year containing around 400 days. Direct physical evidence, preserved in stone, that Earth once spun meaningfully faster than it does now, exactly as the tidal recession of the Moon predicts it should have. 3 independent methods. Laser light bounced off mirrors on the Moon. Ancient eclipse records from human civilizations thousands of years old. And sediment layers laid down hundreds of millions of years before anything resembling a human existed. All converge on the same conclusion. The Moon is moving away. It has been for a very long time, and we can measure it right down to the centimeter every single year. The engine behind at all. How tides slowly push the movie away. The mechanism driving all of this is one of the more elegant, if slightly counterintuitive, pieces of physics in the entire solar system, and starts with something you've likely felt the effects of without ever thinking much about the cause. The ocean tides. Moon's gravity pulls on Earth unevenly. The side of Earth facing the moon at any given moment experiences a slightly stronger gravitational pull than the side facing away, because gravity weakens with distance, and the far side of Earth is, by definition, a little farther from the moon than the near side. This difference in pull, small but real, stretches Earth very slightly, raising a bulge of ocean water on the side facing the moon. And, through a slightly more subtle effect involving the balance of gravitational and rotational forces, a second bulge on the opposite side of the planet as well. This is why most coastlines on Earth experience roughly 2 high tides and 2 low tides each day, as Earth's rotation carries different locations through these 2 bulges. Now here is the crucial detail, the one that drives the entire recession of the moon. Earth rotates on its axis much faster than the moon orbits around it. Earth completes a full rotation in 24 hours. The moon takes about 27.3 days to complete an orbit. Because of this speed difference, Earth's rotation constantly tries to drag the tidal bulges forward, ahead of the moon's actual position overhead. Friction between the moving ocean water and the seafloor, along with friction in Earth's slightly deformable solid body, prevents the bulge from perfectly aligning with the moon at every instant, and instead drags it slightly ahead in the direction of Earth's spin. That slightly ahead bulge of extra mass exerts its own small gravitational pull back on the moon, and because the bulge sits ahead of the moon in its orbital direction, that pull has the effect of gently accelerating the moon forward along its orbit. According to the physics of orbital mechanics, adding forward momentum to an orbiting body doesn't just speed it up. Counterintuitively, it pushes it into a slightly higher, wider orbit, because the added energy goes into raising the orbit's altitude rather than simply increasing its speed at a fixed distance. This is exactly the same principle that allows a spacecraft to raise its orbit around Earth by firing its engines in the direction of travel. Step by step. Earth's fast rotation drags the tidal bulge ahead of the moon. The bulge's gravity gently tugs the moon forward. That forward tug raises the moon's orbit, moving it slightly farther from Earth. And at the same time, by Newton's third law, every action producing an equal and opposite reaction. The moon's pull back on that leading tidal bulge acts as a slight brake on Earth's own rotation, very gradually slowing Earth's spin down. This is why the 2 effects always happen together, locked to one another by the same physical process. As the moon slowly moves away, Earth's rotation is slowly, patiently, being braked. Days on Earth are getting longer, not by an amount you would ever notice in an ordinary lifetime, but measurably, reliably, at a rate of roughly 2 milliseconds per century. It's a big part of why leap seconds occasionally have to be added to official atomic clock time to keep our precise, unchanging atomic timekeeping in sync with Earth slowly, almost imperceptibly, lengthening actual rotational day. Over deep geological time, this effect compounds into something significant. We already mentioned that roughly 620 million years ago, a day on Earth lasted only about 21 hours, going back even further, to shortly after the moon's formation over 4 billion years ago. Some estimates suggest Earth's day may have been as short as 5 or 6 hours, meaning a young Earth spinning several times faster than it does now, experienced sunrise and sunset in a rapid, almost frantic cycle, entirely different from the steady, familiar 24-hour rhythm every form of life on Earth today, including you, has evolved around. And this same mechanism, still operating exactly as it always has, is precisely what continues to push the moon those 3.8 centimeters farther away every single year, indefinitely into the future. At least until certain conditions, which we'll get to later, eventually change. What the moon, the moon, is quietly doing for Earth right now. Before we look forward into the story of the moon's slow departure, it's worth spending time on something easy to take for granted. Everything the moon is doing for Earth, quietly, continuously, right now, tonight, while you listen to this. The most obvious contribution is the ocean tides themselves. The same tidal bulges responsible for pushing the moon away are also responsible for the daily rhythm of rising and falling water along coastlines worldwide, a rhythm that countless marine ecosystems have built their entire life cycles around. Tidal zones, the strip of coastline alternately submerged and exposed as tides rise and fall, are among the most biologically productive habitats on Earth, home to a staggering diversity of organisms adapted specifically to that twice-daily cycle of flooding and draining. Some researchers have even proposed, though this remains a genuinely debated hypothesis rather than settled science, that tidal pools, small, isolated pockets of water repeatedly filled and concentrated by evaporation through tidal cycling, may have played a role in concentrating the chemical ingredients necessary for the origin of life on early Earth, offering a naturally repeating cycle of wetting, drying, and concentrating that some laboratory experiments suggest could help certain prebiotic chemical reactions along. But the moon's most important contributor to Earth's long-term habitability may not be the tides at all. It may be something far less visible: the stabilization of Earth's axial tilt. Earth currently spins on an axis tilted about 23.5 degrees relative to the plane of its orbit around the Sun. That tilt is the entire reason Earth experiences seasons. As Earth orbits the Sun, the tilt causes different hemispheres to receive more or less direct sunlight at different times of year, producing the reliable, predictable cycle of summer, autumn, winter, and spring that essentially all complex life on Earth, including human agriculture and civilization, has been built around. Crucially, that 23.5-degree tilt is not perfectly fixed. Wobbles gently over long timescales, oscillating between about 22.1 and 24.5 degrees across a cycle lasting roughly 41,000 years. One of several slow astronomical rhythms, collectively known as Milankovitch cycles, that influence Earth's long-term climate patterns, including the timing of ice ages over the past several million years. That wobble, though real, is relatively modest and predictable. And one of the primary reasons it stays that modest is the gravitational influence of the moon. The moon's mass and its relatively close orbit exert a stabilizing gravitational influence on Earth's axial tilt, acting somewhat like a gyroscopic weight that resists larger, more chaotic swings in the tilt angle. Without a large moon exerting that steadying influence, computer models suggest Earth's axial tilt could, over millions of years, wander far more dramatically and unpredictably, potentially swinging by tens of degrees, rather than the mild 2.5-degree range we actually experience. Clearest evidence for how dramatic this difference can be comes from looking at Mars. Mars has two moons, Phobos and Deimos, but both are tiny, irregularly shaped bodies, likely captured asteroids. with nowhere near the mass needed to gravitationally stabilize a planet's axial tilt. As a result, computer simulations of Mars's rotational history suggest its axial tilt has likely varied chaotically over millions of years, potentially swinging anywhere from nearly 0 degrees to as much as 60 degrees or more at different points in its history. An almost incomprehensibly unstable range compared to Earth's gentle, predictable wobble. Planet, with a tilt lurching between those extremes, would experience correspondingly chaotic, unpredictable climate swings, sometimes with almost no seasons at all, sometimes with seasons so extreme that entire hemispheres might spend extended periods in near total darkness or near constant, direct sunlight, conditions that would make stable, complex ecosystems and quite possibly complex life itself dramatically harder to sustain over the long term. Earth, by contrast, has enjoyed a comparatively steady, predictable axial tilt for at least the last few 100 million years, and likely for most of its history, largely, according to current planetary science, because of the stabilizing presence of an unusually large moon, relative to the size of its host planet, orbiting close enough to matter gravitationally. In the broader context of comparative planetology, Earth's moon is genuinely unusual. At roughly 1/4 of Earth's diameter, it is by far the largest moon relative to its host planet among all the rocky planets in the solar system. That relative size is not a coincidence of the story we told earlier about a violent glancing collision with a Mars-sized body early in Earth's history. It is a direct consequence of it, and it may be one of the quieter, less appreciated reasons Earth has remained a stable, life-sustaining world for as long as it has. Oh, there is a strange kind of irony sitting at the heart of the moon's story. The very same physical relationship responsible for Earth's centimeter by centimeter lock of its moon is also, and always has been, deeply entangled with the very stability that has allowed Earth's climate, its seasons, and quite possibly its long-term habitability to remain as steady as they have. The moon is not simply a passive companion hanging in Earth's sky. It has been, this entire time, quietly load-bearing, the near future. What changes on human and civilization timescales. Let's shift now from the deep past into the future, starting with changes close enough, in relative terms, that they sit within time. Hale's human civilization, or at least human science, can meaningfully track and plan around. On any timescale relevant to a single human life, the effects of the moon's recession are, frankly, imperceptible. 3.8 centimeters a year is not something you, or your children, or even many future generations down the line, will ever notice directly. The moon in the sky tonight will look, for all practical purposes, identical to the moon your great-great-grandchildren will see. This is not a story about anything changing quickly, but stretched across thousands, and then millions of years. Certain effects become measurable, and eventually, quite dramatic. The most immediate, ongoing effect is the continued, gradual lengthening of Earth's day, driven by the same tidal braking we described earlier. At the current rate of roughly 2 milliseconds added per century, it would take about 50,000 years just to add a single extra minute to the length of Earth's day. Again, not something anyone will consciously experience, but a real, physical, ongoing process, continuously logged and confirmed by the precise atomic clocks and astronomical observations modern science relies on. One of the more specific, well-studied, and genuinely fascinating consequences of the moon's recession involves something that many people find surprisingly moving once they learn about it: the eventual end of total solar eclipses. Total solar eclipse the awe-inspiring astronomical event where the moon passes precisely between Earth and the sun, completely blocking the sun's bright disk and revealing its faint, ghostly outer atmosphere, the corona, is only possible because of an extraordinary, almost eerie coincidence in the present-day solar system. The sun is about 400 times larger in diameter than the moon, but it also happens to sit, at this particular point in solar system history, about 400 times farther from Earth than the moon does. That precise coincidental ratio means the sun and moon appear from Earth's surface as almost exactly the same apparent size in the sky, close enough that the moon can, under the right alignment, completely cover the sun's bright disk without either object appearing dramatically larger or smaller than the other. This is not a permanent arrangement. As the moon continues its slow recession, its apparent size in Earth's sky continues to shrink, ever so slightly, year after year. Eventually, astronomers estimate roughly 600 million to 1 billion years from now, depending on the precise assumptions used in the calculation. The moon will have receded far enough that its apparent disk will no longer be large enough to fully cover the sun's disk during an eclipse, even at the moment of most precise alignment. From that point onward, every solar eclipse Earth experiences will be what's known as an annular eclipse, a ring of fire event, where a thin, brilliant ring of the sun's surface remains visible around the edges of the moon's disk, rather than being fully blocked out. Total solar eclipses, in the dramatic, complete, corona-revealing sense that has captivated human observers for as long as we have written history, will end permanently. It's a strange thing to consider. Total solar eclipses are not a permanent feature of Earth's sky, guaranteed by the basic architecture of the solar system. They are a temporary, almost coincidental gift, available only during a particular multi-billion-year window in the Earth-Moon system's long history, a window we happen to be living inside of right now, along with every human being who has ever lived. And, unless something changes dramatically about the pace of the moon's recession, every human being who will live for roughly the next 500 million to billion years as well. The deep future. Does the moon ever actually leave? Here is a question worth sitting with slowly, because the answer is more interesting and more strange than a simple yes or no. Does the moon's recession ever stop? Does it simply keep drifting outward, farther and farther, until it escapes Earth's gravity entirely and disappears into its own independent orbit around the sun? The answer, according to current orbital physics, is no. Not in the way that question implies. The moon's recession is not an unlimited, ever-accelerating process heading toward escape. It is, instead, heading toward a very specific, very stable endpoint, a state called mutual tidal locking, sometimes described as a double-locked or synchronous system. We are already partway there, in one direction. The moon has been tidally locked to Earth for a very long time. It always shows the same face toward Earth, the familiar pattern of dark and light patches that has looked identical to every human observer throughout recorded history, because the moon's own rotation period exactly matches its orbital period around Earth. This is not a coincidence. It is the result of Earth's gravity over billions of years, having gradually slowed the moon's original, faster rotation down to match its orbit. Through the same basic tidal friction mechanism described earlier, just acting in the opposite direction. Earth's gravity breaking the moon's spin, rather than the moon's gravity breaking Earth's. Earth, meanwhile, is undergoing the same process in reverse, just far more slowly, because Earth is much more massive than the moon, and therefore much harder to tidally break. as Earth's rotation continues to slow. That steady lengthening of the day we discussed earlier. And as the moon continues to recede, the system as a whole is very gradually moving toward a theoretical end state where Earth's rotation period and the moon's orbital period would eventually match each other exactly, just as the moon's rotation and orbital period already match today. At that hypothetical point, Earth's day would have lengthened dramatically. Some calculations suggest to somewhere in the range of 40 to 50 of our current days, and the moon would appear to hang motionless in the sky from any given point on Earth's surface, always in the same position, exactly the way Earth's geostationary communication satellites appear to hover motionless above a fixed point on Earth's surface today. Half of Earth would permanently see the moon in the same spot in the sky, day after day, year after year. The other half would never see it at all. That is the theoretical endpoint of the current recession process. Not an escaping moon, drifting off into deep space, but a slowing, locking system, settling into a mutual, synchronized embrace, where the tidal forces driving the recession finally balance out, and the outward drift stops on its own, however. And this is the detail that makes the story genuinely more interesting than a tidy, permanent ending. Most careful calculations suggest Earth and the moon will not actually reach that fully locked state before something else happens first, something entirely unrelated to the moon itself. The sun's own evolution, reaching full mutual tidal lock, is estimated to take on the order of 50 billion years or more, depending on the specific model used, a timescale dramatically longer than the roughly 5 billion years the sun has left in its own life cycle before it changes so significantly that Earth's environment, and quite possibly the Earth-Moon system, basic architecture, will be transformed by an entirely different process altogether. In other words, the moon's recession will very likely never actually finish, in the sense of comfortably arriving at a peaceful, stable, locked endpoint. Long before that could happen, the sun itself is expected to intervene. How the sun changes the story roughly 5 billion years from now, having spent the vast majority of its main sequence lifetime fusing hydrogen into helium in its core. Our sun will begin to run low on hydrogen fuel at its center. When that happens, according to well-established stellar physics, the sun's core will contract and heat further, while its outer layers dramatically expand and cool, transforming the sun from the stable, modest yellow-white star we know today into a vastly larger, cooler, redder star, a red giant. Estimates vary somewhat depending on the details of the model used, but many calculations suggest the sun, in its red giant phase, could expand to a diameter roughly 200 times its current size, potentially large enough to engulf the orbits of Mercury and Venus entirely, and, in some models, to reach uncomfortably close to Earth, current orbital distance, or even engulf Earth itself, depending on precisely how much mass the sun loses through stellar winds in the process, which affects how far the remaining planet's orbits shift outward in response. Whether or not Earth itself is physically engulfed by the expanding sun remains a genuinely open question among astrophysicists, with different models reaching different conclusions depending on their assumptions. But what is far less ambiguous is that Earth's environment, long before the sun's red giant phase even fully arrives, will already have become catastrophically hostile. The sun's total luminosity is expected to increase enormously in the lead-up to the red giant phase, increasing gradually over the next roughly 1 billion years to the point, as discussed in the context of Venus's own history, where Earth's oceans are expected to begin evaporating in a runaway greenhouse process disturbing, lies similar to what already happened to Venus billions of years ago. By the time the sun actually reaches its red giant phase, Several billion years further still, Earth is expected to already be a scorched, lifeless world, its oceans long gone, regardless of whether the expanding sun physically swallows it or not. And the moon, throughout all of this, the honest answer is that the moon's fate becomes deeply entangled with whatever happens to Earth itself. If Earth is engulfed by the sun's expanding outer atmosphere, current models generally expect the moon, orbiting so closely, to be engulfed as well, likely not long afterward, as its orbit decays rapidly within the drag of the sun's tenuous outer layers. If Earth narrowly survives, pushed outward by the sun's mass loss into a wider, if scorched and lifeless, orbit, the moon would likely continue orbiting alongside it, an ancient, silent companion, circling a dead planet around a swollen, dying star, the final quiet chapter in a relationship that began billions of years earlier, in the fire and debris of a completely different kind of collision entirely. Either way, the roughly 3.8 centimeters of drift the moon experiences this year, and every year, is not part of a story that ends peacefully on its own terms in some tidy, gravitationally balanced future. It is a slow, ongoing process, quietly running in the background of an even larger, even slower story, the life and eventual death of the star that made all of this, Earth, moon, tides, seasons, and everything alive today, possible in the first place. Life on Earth, quickly shaped by the moon long before any human being understood TID, or physics, or lunar laser ranging, or the giant impact hypothesis. Life on Earth had already been shaping itself around the rhythms of the moon on for hundreds of millions of years. A quiet, biological entanglement that continues today, largely invisible to us, but deeply woven into ecosystems around the world. Perhaps the most well-documented example is coral spawning. Many coral species across reef systems worldwide synchronize mass spawning events, releasing eggs and sperm into the water in enormous coordinated bursts to specific phases of the lunar cycle, often clustering tightly around a particular number of nights after the full moon. On Australia's Great Barrier Reef, this phenomenon produces one of the most dramatic synchronized reproductive events in the natural world. On just a handful of nights each year, timed with remarkable precision to lunar phase, sea temperature, and day length together, vast stretches of reef release their spawns simultaneously, turning the water into what researchers have described as an underwater snowstorm, visible from the surface. Exactly how corals sense and synchronize to moonlight, this precisely remains an active area of research, with evidence pointing to specialized light-sensitive proteins that may allow coral polyps to detect the subtle differences between moonlight and starlight, distinguishing lunar phase with a sensitivity that still surprises the scientists who study it. Sea turtles offer another striking example. Female sea turtles typically nest at night on beaches, and hatchlings that emerge from their buried nests rely heavily on light cues to find their way to the ocean. Historically, moonlight, reflecting off the water's surface, was likely one of the primary directional cues guiding newly hatched turtles away from land and toward the safety of the sea, a natural signal that predates artificial lighting by tens of millions of years. In recent decades, this ancient, moonlight-based navigation system has become a genuine conservation concern, as artificial lighting from coastal development increasingly disorients hatchlings, drawing them inland, away from the ocean, toward artificial light sources. Their navigation instincts were never built to distinguish from moonlight. Beyond individual species, some researchers have explored whether certain broader biological rhythms in humans and other mammals show any residual connection to lunar lunar cycles, questions around sleep patterns, menstrual cycle length, or nocturnal animal behavior, sometimes loosely tied to lunar phase, in popular discussion. Worth being careful and precise here. The scientific evidence for a direct, reliable lunar influence on human sleep or behavior remains genuinely mixed, and, in many specific claims, unsupported by rigorous data. Unlike the very well-documented cases in marine species such as corals and turtles, where the lunar connection has been established through careful, repeated, controlled observation. What is well established, though, is the broader ecological principle. The moon's gravitational pull on Earth's tides and the moon's contribution of reflected sunlight to otherwise dark nights have been continuous, reliable environmental signals for essentially the entire history of complex life on Earth and evolution over hundreds of millions of years. Tends to make use of whatever reliable signals happen to be available. There is something worth quietly noticing in all of this. The same object slowly receding those 3.8 centimeters a year. The same object whose gravity is patiently lengthening Earth's days is also the same object that countless species across hundreds of millions of years of evolutionary history have quietly built their most fundamental reproductive and survival behaviors around. Coral reefs releasing their spawn on a handful of precisely timed nights each year. Sea turtle hatchlings finding the ocean in total darkness, guided by a pale reflection in the sky. All of it entangled with the same slow, patient astronomical relationship we've been tracing all along. Humanity's relationship with the moon. Human beings, too, have spent the entirety of our history quietly organizing ourselves around the moon's rhythm, long before anyone understood the physics driving it. Some of the earliest known calendar systems, across entirely separate and unconnected civilizations, were lunar or lunisolar in structure, tracking time by a roughly 29.5-day cycle from one new moon to the next, a period easy to observe directly with the naked eye, long before any more precise astronomical tools existed. The Babylonian calendar, ancient Chinese calendars, the Islamic Hijri calendars still in use today, and the Hebrew calendar all incorporate lunar cycles directly into their structure, in some cases still actively determining the timing of religious observances and festivals in the present day, thousands of years after those calendar systems were first established. Many ancient agricultural societies tracked planting and harvesting seasons, partly through lunar observation, particularly in cultures without written astronomical records, where the visibly changing shape of the moon offered a simple, universally accessible way to track the passage of roughly a month at a time. The moon also played a direct, practical role in one of humanity's oldest and most important skills: navigation. Before satellite positioning systems, sailors across many seafaring cultures used the moon, alongside the sun and stars, as a celestial reference point for determining position and direction at sea, a skill so essential that entire navigational traditions, from Pacific Islander wayfinding to European celestial navigation techniques, were built substantially around interpreting the moon's position, phase, and movement relative to the horizon and stars. And then, in the 20th century, humanity's relationship with the moon changed in a way no earlier civilization could have anticipated. We went there ourselves. The Apollo program, culminating in Apollo 11's landing in July 1969, remains, more than half a century later, one of the most significant technological and human achievements in history. 12 astronauts, across 6 successful landing missions between 1969 and 1972, walked on the surface of another world, collected and returned nearly 400 kilograms of lunar rock and soil samples to Earth, and, almost incidentally to their primary scientific goal, left behind the retroflector arrays that would go on to give us, decades later, our precise, ongoing measurement of the moon's slow recession, a scientific legacy those astronauts could not have fully anticipated at the time, quietly continuing to generate new data with every laser pulse fired at the moon. More than 50 years after the missions themselves ended, human interest in the moon has not ended with Apollo. Multiple space agencies and private companies are, as of this decade, actively planning renewed lunar exploration. NASA's Artemis program aims to return astronauts to the lunar surface with an eventual goal of establishing a sustained human presence, potentially including a long-term lunar base. While other national space agencies, including those of China and India, have pursued increasingly ambitious robotic and eventually crewed lunar missions of their own. There is a strange, quiet resonance in the timing, as our scientific instruments become sensitive enough to measure the moon's centimeter by centimeter departure with ever-increasing precision. Humanity's practical, hands-on relationship with the moon is, if anything, deepening rather than fading, moving toward a future that may eventually include permanent human habitation on a world that has, for the entirety of our species' existence so far, only ever been observed from a distance. A strange cosmic contrast. The moon that's doing the opposite. It's worth pausing here to notice something that makes Earth's moon even more distinctive. Not every moon in the solar system is moving away from its planet. Some are doing exactly the opposite, spiraling slowly, steadily inward toward eventual destruction. The clearest example sits right next door, around Mars. Phobos, the larger and closer of Mars's two small moons, orbits at a distance of only about 6,000 kilometers from the Martian surface, so close that it completes a full orbit around Mars in just 7 hours and 39 minutes, faster than Mars itself rotates on its axis. Because Phobos orbits faster than Mars spins, the same tidal mechanism that pushes our moon away from Earth works in reverse for Phobos. The tidal bulge Phobos raises on Mars lags behind Phobos' own position, rather than being dragged ahead of it, and that lagging bulge exerts a gravitational pull that slowly drains orbital energy from Phobos, rather than adding it. The result: Phobos is spiraling slowly inward, losing roughly 2 meters of altitude every 100 years. Current models suggest that within somewhere between 30 and 50 million years, Phobos will have spiraled close enough to Mars that it either crashes directly into the Martian surface, or, more likely according to most current models, is torn apart by Mars's tidal forces before ever reaching the ground. Its gravitational pull no longer strong enough to hold itself together against the increasingly intense stretching forces of Mars's gravity as it draws closer, likely shattering into a ring of debris encircling Mars, similar in concept, though far smaller in scale, to the rings of Saturn. The difference between Phobos' fate and our moon's fate comes down entirely to that one critical detail. Whether a moon orbits faster or slower than its host planet rotates, our moon orbits Earth slower than Earth spins, so the tidal bulge is dragged ahead of the moon, adding energy to its orbit and pushing it outward. Phobos orbits Mars faster than Mars spins, so the tidal bulge lags behind Phobos, draining energy from its orbit and pulling it inward. Two moons, two neighboring planets, and two completely opposite long-term fates, dictated by nothing more than the relative speeds of rotation and orbit at this particular point in each system's history. It's a useful reminder that moons slowly moving away from their planets is not some universal, guaranteed rule of celestial mechanics. It is a specific outcome, dependent on specific orbital conditions that, in Earth's case, happen to be pushing our moon outward, while in Mars's case, are pulling its largest moon inexorably toward eventual destruction. What if Earth never had a moon at all? There is one more way to appreciate what the moon means to Earth, and it involves imagining its complete absence. Not a receding moon, slowly drifting farther away over billions of years, but a version of Earth that formed without ever acquiring a large moon in the first place. The way Venus and Mercury, Earth's rocky neighbors, both did, without the catastrophic, glancing collision with Theia early in Earth's history. Most models suggest Earth would likely still have ended up with some moons, if any at all, but almost certainly nothing resembling the large, close, massive moon we actually have. Perhaps small, captured asteroids, similar to Mars's Phobos and Deimos, or perhaps no moon at all, similar to Venus and Mercury. The most significant consequence, based on the models discussed earlier, would very likely involve Earth's axial tilt. Without the moon's substantial, stabilizing gravitational influence, Earth's tilt would likely have been subject to the same kind of chaotic, unpredictable variation modeled for Mars, potentially swinging across tens of degrees over millions of years, rather than gently oscillating within our actual, narrow 2.5 degree range. A planet experiencing that kind of chaotic tilt would likely experience correspondingly chaotic, unpredictable long-term climate patterns, sometimes with mild, Earth-like seasons, but at other points in its cycle, potentially extreme, disorienting shifts between near total axial tilt and almost no tilt at all, producing climate instability on a scale far beyond anything Earth's actual climate history has experienced, independent of, and in addition to any human-caused climate change occurring today. Tides would also look dramatically different. Without the moon, Earth's tides would be driven almost entirely by the sun alone. Real, but considerably weaker than the combined lunar and solar tides Earth experiences today, since the sun, despite being vastly more massive than the moon, is also vastly farther away, and tidal force weakens rapidly with distance in a way that lets the much closer moon dominate Earth's actual tidal behavior, even though it is a tiny fraction of the sun's mass. Weaker, more modest tides would likely have meant less pronounced, less biologically rich tidal zones along coastlines, potentially altering, in ways difficult to fully model, the evolutionary pressures and opportunities available to early marine life during the critical periods when complex, multicellular life was first developing on Earth. Earth's day length would also almost certainly be different, likely spinning considerably faster than the current 24-hour rotation, since the tidal braking effect that has slowed Earth's spin over billions of years has been driven overwhelmingly by the moon rather than the sun. Some estimates suggest a moonless Earth might still be rotating with a day length closer to the 6 to 10 hour range that characterized our actual young moon-having Earth billions of years ago, implying that much of the slow, patient lengthening of Earth's day that has already occurred throughout our real history has been, in a very direct sense, gift, or perhaps more accurately a side effect, of the moon's presence and its ongoing gravitational relationship with our planet. None of this is meant to suggest life could never have arisen on a moonless Earth. That remains a genuinely open scientific question, and there is no scientific consensus that a large moon is a strict, universal requirement for a planet to develop and sustain complex life elsewhere in the universe. But it does suggest that the specific, familiar Earth we actually live on, its particular tides, its particular 23.5 degree tilt, its particular 24-hour day, its particular pattern of gentle, predictable seasons, is deeply, specifically entangled with the presence of an unusually large moon, born from an unusually violent collision early in a solar system that could very easily have unfolded without either event occurring at all. To Q8 accounting behind at all. Angular momentum. Underneath everything we've described so far, the receding moon, the lengthening day, the eventual slow march toward mutual tidal lock, sits a single, elegant principle from physics that ties the whole story together. The conservation of angular momentum. Angular momentum is, in simple terms, a measure of how much rotational motion a system contains, combining how fast something spins or orbits with how its mass is distributed relative to its center of rotation. One of the deepest, most reliable laws in all of physics states that, within a closed system, one not exchanging energy or momentum with anything outside itself, total angular momentum is conserved. It cannot be created or destroyed. It can only be transferred, redistributed, moved from one part of the system to another. The Earth-Moon system, for the purposes of this story, behaves essentially as a closed system. The total angular momentum contained within it, Earth's spin plus the Moon's orbit around Earth, stays constant over time, even as the split between those two components continuously shifts. As Earth's rotation gradually slows, losing angular momentum from its spin, that lost angular momentum does not simply vanish. It is transferred, through the tidal interaction we described earlier, directly into the Moon's orbit, which is precisely why a slowing Earth and a receding Moon are not two separate coincidental trends, but two halves of a single, continuous, physically necessary exchange. Every fraction of a millisecond added to the length of Earth's day corresponds, with mathematical precision, to a matching, calculable increase in the Moon's orbital distance. This is also, in a sense, the underlying reason the process has a natural, physically necessary endpoint at all. The theoretical state of mutual tidal lock we discussed earlier represents the specific configuration where Earth's spin and the Moon's orbit have reached the same angular velocity, at which point the tidal bulge no longer lags or leads at all, sitting perfectly aligned beneath the Moon, and the entire transfer mechanism driving both effects simply switches off because there is no more alignment left to generate the gravitational tug responsible for moving momentum between the two components of the system. It is, in its own quiet way, one of the more beautiful examples in all of planetary science of a single, simple conservation law playing out over billions of years on a scale large enough to reshape the length of a day, the visibility of eclipses, and the distance to the Moon itself. All of it simply bookkeeping and angular momentum sliding patiently from one side of an old, ongoing ledger to the other, exactly as the laws of physics require it to be. T-ski itself, slowly changing. Let's return, for a while, to simply picturing what all of this looks like, slowly, across deep time. Not through equations, but through the sky itself, changing by degrees too small to notice within a human life, but real nonetheless. Night. The Moon appears in Earth's sky at an average angular size of about half a degree, roughly the width of your smallest fingertip, held at arm's length. That apparent size has been slowly shrinking by an amount too small to ever measure with the naked eye for the entire span of human civilization, and for a very long time before that as well. A few 100 million years ago, in the age of the dinosaurs, the Moon would have appeared noticeably larger in the sky than it does tonight. Not dramatically so, not the vast, looming presence of its earliest days shortly after formation, but detectably larger. If you could somehow stand there with a modern instrument to measure it precisely. Moonlight itself would have been correspondingly brighter in that ancient sky. A closer moon, reflecting the same sunlight back toward Earth across a shorter distance, results in more light reaching Earth's surface, all else being equal, meaning the ancient nights of Earth's deep past were, in a very direct, physical sense, less dark than the nights we experience now, illuminated by a larger, closer, brighter moon than any human being has ever actually witnessed. Moving in the other direction, into the deep future, the trend simply continues. Hundreds of millions of years from now, the moon will hang perceptibly smaller and dimmer in Earth's sky than it does tonight. Still clearly visible, still cycling through its familiar phases, still governing tides, still, for a very long stretch of that future, still capable of producing the near-perfect solar eclipse alignment we discussed earlier, right up until the point 600 million to a billion years out, when that alignment finally, permanently breaks and total solar eclipses end. There is a strange, quiet privilege buried in the timing of when we happen to be alive to witness all of this. The moon we see tonight sits, cosmically speaking, in an unusually favorable window, close enough to still produce dramatic, complete solar eclipses, far enough remote from its violent, chaotic origin that its orbit has settled into the calm, predictable, nearly circular path we rely on for our calendars and our tides, and stable enough, for now, that none of the deep, slow changes described throughout this documentary will meaningfully alter the sky above you, or above anyone you will ever know, in any way you could actually perceive. Other moons, other stories. It's worth taking a slightly wider view here, out across the rest of the solar system, because Earth's moon and Mars's doomed Phobos are far from the only examples of large moons living out dramatic, long-term orbital stories of their own. Neptune's largest moon, Triton, offers one of the most striking examples of orbital instability anywhere in the solar system. Unlike almost every other large moon, Triton orbits Neptune backwards, in a direction opposite to Neptune's own rotation, a strong indication that Triton was not born alongside Neptune the way our moon was born alongside Earth, but was instead a captured object, likely a former dwarf planet, similar in composition to Pluto, gravitationally seized by Neptune sometime after both bodies had already formed independently, out in the distant, frigid reaches of the outer solar system. Because Triton orbits in the wrong direction relative to Neptune's spin, the same fundamental tidal physics that pushes our moon outward instead works to drag Triton unsteadily inward, similar to Phobos' fate around Mars, but on a far larger scale. Current estimates suggest that somewhere between 3.5 billion years from now, Triton will have spiraled close enough to Neptune to be torn apart by tidal forces, likely forming a spectacular ring system around Neptune, considerably more massive and dramatic than the rings Saturn currently displays. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, collectively known as the Galilean moons, after their discoverer Galileo Galilei, who first observed them in 1610. Present an entirely different kind of long-term story, one dominated less by orbital drift and more by intense, ongoing tidal heating. These moons exist in a delicate gravitational relationship with each other and with Jupiter, called orbital resonance, where their orbital periods lock into simple whole number rating os with one another. That resonance keeps their orbits slightly stretched or eccentric, rather than settling into perfectly circular paths, and that ongoing stretching, driven by Jupiter's immense gravity, generates enormous internal heat through friction inside each moon. Heat dramatic enough to make Io the most volcanically active body anywhere in the solar system, its surface constantly resurfaced by continuous eruptions, and heat believed to maintain a liquid, potentially habitable subsurface ocean beneath the icy crust of Europa. One of the most actively studied and scientifically promising targets in the entire search for life beyond Earth. Saturn's rings themselves may represent yet another version of a moon's long-term fate, playing out on a timescale already largely completed rather than still unfolding. Growing body of scientific evidence, including detailed measurements from NASA's Cassini mission before it concluded in 2017, suggests Saturn's spectacular ring system may be relatively young in astronomical terms, potentially just a few 100 million years old, rather than as old as the solar system itself, and may have formed from the tidal destruction of a former moon or a close encounter between multiple icy moons that came too close to Saturn and was torn apart by the same kind of tidal forces expected to eventually destroy Phobos and Triton. Yet against this wider backdrop, Earth's moon stands out as something genuinely unusual. A large moon, born in a violent, singular collision, rather than captured or built through resonant heating, settled into a stable, outward drifting orbit, rather than a doomed, inward spiral, and, at least for the next several 100 million years, essentially safe from the kind of dramatic tidal destruction awaiting Phobos, Triton, and whatever moon or moons may have once orbited closer to Saturn. Standing in the future, a slow walk across deep time. Let's course deep time. Let's slow down again, one more time, and simply walk through what Earth's relationship with its moon might look and feel like at a series of distant points stretched out across the deep future, not as rigorous prediction, but as a quiet, careful visualization grounded in everything we've discussed so far. 100 million years from now, the moon has receded a little over 3.5 kilometers farther than it sits tonight. Still, in practical terms, indistinguishable to the naked eye from the moon you know now. Earth's day has lengthened by perhaps a couple of minutes compared to today. Coral reefs, if they still exist in a form resembling today's, in a climate and ocean chemistry that will likely look considerably different after 100 million years of geological and biological change, are still very possibly timing their spawning to the same lunar phases their ancestors used tonight. Total solar eclipses still occur, still dramatic, still complete, still capable of turning day briefly into a strange corona-lit twilight. 500 million years from now, the moon has receded roughly 19 kilometers farther than its current distance. Still a small fraction of the total distance involved, still not enough to end total solar eclipses, though the margin has narrowed considerably, and the longest, most complete eclipses possible today are likely no longer achievable, with only the closest possible lunar approaches still capable of producing a full eclipse. Earth's day has lengthened by perhaps 10 to 15 minutes compared to tonight. The sun itself has grown modestly brighter than it appears now, part of its slow billion-year march toward the eventual runaway greenhouse threshold discussed earlier. A threshold still safely in the future at this point, but closer than it was. 1 billion years from now, we arrive at the range most commonly cited for the true end of total solar eclipses, as the moon's apparent size finally shrinks below the threshold needed to fully cover the sun's disk, even at closest approach. From this point onward, forever, every eclipse Earth experiences is an annular one, a ring of fire rather than a full corona. This is also, according to the climate models discussed earlier, roughly the era when Earth's oceans are expected to begin their own runaway evaporation, driven by the sun's steadily increasing brightness. meaning the ending of total solar eclipses and the beginning of Earth's transformation into something more like modern Venus, are expected to arrive. In the vast, patient timescale of this story, at roughly the same broad chapter, two separate consequences of the same slowly brightening star, unfolding side by side, and further still, 5 billion years, 6 billion years, into the sun's eventual red giant phase, Earth and the moon beside it arrive at whatever ending the details of stellar mass loss and orbital mechanics ultimately assign them. Engulfment or a scorched, airless survival in a wider, colder lit orbit around a swollen, dying star, the moon still faithfully circling closer to Earth in relative terms than it ever will be again once true mutual lock is reached. But by then genuinely academic, a detail in a story that has, by that point, moved on to questions far larger than the distance between one planet and its one moon. None of this, again, is a story that touches your life, or the life of anyone you love, or the life of human civilization as we currently understand it, in any direct way. It is simply the shape of the road ahead. Long, slow, almost unimaginably patient, unfolding in centimeters a year, exactly as it always has, exactly as it will continue to, long after every detail of this particular telling of the story has been forgotten. How confident are scientists? Really, a note on uncertainty. It's worth taking a moment, calmly and honestly, to talk about how confident scientists actually are in the different pieces of this story. Because not every claim we've covered tonight carries the same level of certainty, and a good, trustworthy account of any scientific topic should be honest about that difference, rather than presenting everything with equal, unwavering confidence. Some of what we've described tonight is about as certain as anything in observational science gets. The moon's recession rate of 3.8 centimeters per year is not a model, a theory, or an estimate in the uncertain sense. It is a direct, repeated, physical measurement, verified continuously for over 50 years through lunar laser ranging, cross-checked independently through ancient eclipse records, and geological tidal rhythmite data, the basic tidal mechanism responsible for that recession. The lag of Earth's tidal bulge, the transfer of angular momentum from Earth's spin to the moon's orbit, is grounded in extremely well-established, thoroughly tested physics, understood with high confidence. Other parts of the story carry somewhat more uncertainty, though still well within the range of solid mainstream scientific understanding. Giant impact hypothesis for the moon's formation is the leading model, strongly supported by multiple independent lines of evidence. But it is not the only model that has ever been proposed, and researchers continue to refine the details, the exact size and composition of Theia, the exact timeline of the moon's accretion from the resulting debris disk, and certain specific isotopic puzzles that don't fit the simplest version of the model perfectly. It remains the scientific consensus, the best supported explanation available. But best supported explanation is a slightly different, appropriately more humble claim than settled, unchangeable fact. Predictions about the deep future carry the most uncertainty of all, simply because they require extrapolating known physics across timescales of hundreds of millions to billions of years, layering multiple interacting systems, Earth's rotation, the moon's orbit, the sun's own stellar evolution, on top of one another, each with its own margin of error that compounds the further into the future the prediction reaches. The broad shape of the story: continued recession, a lengthening day, the eventual end of total solar eclipses, an eventual approach toward mutual tidal lock that the sun's evolution likely interrupts first, reflects genuine scientific consensus about the underlying physics. But specific numbers, like 600 million to 1 billion years for the end of total eclipses, or 50 billion years for theoretical full tidal block, are best understood as informed estimates, calculated from our best current models, rather than fixed, precise dates carved into the structure of the universe. This is not a weakness in the story. It is, if anything, part of what makes it trustworthy. Real science, done honestly, comes with acknowledged uncertainty, refined over time as better instruments, better models, and new missions like Davinci, Veritas, and Envision at Venus, or continued lunar laser ranging and future lunar missions closer to home, continue to sharpen the picture. Core, well-supported facts of tonight's story: a receding moon, a slowing Earth, an ancient, violent birth, and a future shaped by the same physics we can measure with confidence tonight, are about as solid as science gets. The precise dates and distant details remain, appropriately, open to refinement, exactly as good science should be. A quick recap for those drifting in and out. If you've been drifting in and out of sleep through parts of this, here is a slow, simple recap of the core shape of the story, gathered together gently in one place. The moon formed roughly 4.5 billion years ago, out of debris thrown into orbit around Earth by a catastrophic, glancing collision with a Mars-sized protoplanet called Theia. It formed close to Earth, initially, perhaps 10 to 20 times closer than it sits today. And Earth itself, in that ancient era, spun far faster than it does now, with days lasting only a handful of hours. Ever since that early period, ocean tides raised by the moon's gravity, dragged slightly ahead of the moon's position by Earth's faster rotation, have been gently pulling the moon forward along its orbit, raising it into a slightly wider path, while simultaneously acting as a brake on Earth's own spin. This single mechanism, the conservation of angular momentum, sliding from Earth's rotation into the moon's orbit, explains both the moon's steady recession, currently measured at 3.8 centimeters per year, and the slow ongoing lengthening of Earth's day, roughly 2 milliseconds added per century. Along the way, the moon has quietly stabilized Earth's axial tilt, keeping our seasons mild and predictable across hundreds of millions of years, in sharp contrast to the chaotic, wildly varying tilt believed to characterize Mars, a planet with no comparably large moon to provide the same gravitational steadying influence. Marine life, from coral reefs to sea turtles, has built essential reproductive and navigational behaviors around the moon's light and its tides across hundreds of millions of years of evolutionary history. And human civilizations across every corner of the globe have built calendars, religious observances, agricultural timing, and entire navigational traditions around the same pale, reliable object in the sky. Looking forward, the moon's continued recession will, on a timescale of roughly 600 million to 1 billion years, permanently end the era of total solar eclipse on Earth, as the moon's shrinking apparent size in the sky falls below the threshold needed to fully cover the sun's disk. On a much longer timescale still, Earth and the moon are technically moving toward a theoretical state of mutual tidal lock, but that state is expected to take tens of billions of years to fully arrive, far longer than the roughly 5 billion years remaining before the sun itself evolves into a red giant, engulfing or scorching Earth, long before the Earth-Moon system ever reaches that quiet, locked equilibrium on its own. Elsewhere in the solar system, not every moon shares Earth's fate. Mars's moon Phobos and Neptune's moon Triton are both spiraling slowly inward, doomed, on timescales of tens of millions to a few billion years, to eventual tidal destruction, most likely forming rings around their host planets rather than crashing directly into the surface. And underneath all of it, tonight, right now, none of this is moving fast enough to matter to you, or to anyone you know, in any way you will ever be able to perceive directly. The moon in the sky above you tonight is, for all practical human purposes, exactly the same moon your ancestors saw, and exactly the same moon your descendants, for hundreds of thousands of generations to come, will see as well. Questions people often ask about the moon's slow departure. Let's spend some time now on a few of the questions people most commonly ask once they first learn the moon is moving away. Gentle, simple answers gathered here to round out the picture. Will the moon ever completely disappear from Earth's sky? No. Based on current orbital physics, the moon is not on a trajectory to escape Earth's gravity and drift away into an independent orbit around the sun. It is moving toward a much gentler, much more stable outcome, a theoretical state of mutual tidal lock, where the recession itself gradually slows and eventually stops, long before the moon could ever become distant enough to escape Earth's gravitational hold entirely. The sun's own evolution, several billion years from now, is expected to disrupt the Earth-Moon system long before the moon could reach any kind of true, permanent departure on its own. Will people alive today ever notice any difference at all? No, not directly, and not through casual observation. 3.8 centimeters a year is a change so small that even the most careful amateur astronomer, using standard equipment, could not detect it across an entire human lifetime. Only extremely precise scientific instruments, laser ranging systems accurate to millimeters, atomic clocks sensitive to fractions of a second, are capable of detecting the ongoing recession and the associated lengthening of Earth's day at all. Does the moon's recession have anything to do with human-caused climate change? No. These are entirely separate, unrelated phenomena, driven by completely different physical processes. The moon's recession is a gravitational, tidal effect, operating continuously regardless of anything happening in Earth's atmosphere, and has been occurring at essentially the same steady rate for a very long time, long before human civilization existed at all. Climate change, by contrast, is driven by the composition of Earth's atmosphere and the greenhouse gases within it, a separate process entirely, operating on a vast, faster human-relevant timescale, and not meaningfully connected to the moon's slow orbital drift in any direct causal way. Do other planets in the solar system have moons that behave the same way ours does? Some do, some don't, depending on the specific orbital relationship between each moon and its host planet. As discussed earlier, Mars's Phobos and Neptune's Triton are both spiraling inward rather than outward, doomed to eventual tidal destruction rather than a gentle, stable recession. Jupiter's Galilean moons experience yet another dynamic entirely, dominated by mutual orbital resonance and intense tidal heating rather than steady inward or outward drift. Earth's moon's specific pattern, steady outward recession, heading toward a theoretical stable equilibrium, is a genuine, specific outcome of Earth's particular rotation speed and the moon's particular orbital characteristics, not a universal rule shared by every large moon in the solar system. Could scientists be wrong about all of this? As with any area of active scientific research, refinement is always possible, and researchers continue to improve their models with new data from ongoing lunar laser ranging, from renewed lunar missions, and from improved understanding of Earth's own deep geological history. but the core measurement at the heart of tonight's story. The moon's recession rate of 3.8 centimeters per year is one of the most precisely and repeated, confirmed measurements in all of planetary science, verified independently through multiple, completely different methods over more than 50 years. It is about as reliable a scientific fact as exists in this field. On last slow look upward, we're coming now toward the end of tonight's story. Let's spend these last few minutes simply looking upward, slowly, one more time, gathering together everything we've walked through tonight into a single, quiet picture. Somewhere above you tonight, whether visible through a window, hidden behind clouds, or simply present in the sky beyond whatever ceiling happens to be over your head right now. The moon continues along the same orbit it has followed for billions of years, 384,000 kilometers away, drifting outward at the same patient 3.8 centimeters per year. It has maintained for longer than there has been anyone anywhere to measure it. It is the same moon that hung, much closer and much larger, over an Earth still cooling from its own violent formation, over oceans that had not yet finished condensing from a searingly hot young atmosphere, over a planet spinning so quickly that a single day passed in only a handful of hours. It is the same moon that later hung, still closer than today, over the shallow tidal pools where some researchers believe the earliest chemistry of life may have first begun concentrating itself into something more complex. It is the same moon that guided sea turtle hatchlings toward the ocean, that triggered synchronized coral spawning across ancient reefs, that Babylonian astronomers recorded eclipses of on clay tablets, that Pacific Island navigators used to cross vast stretches of open ocean, that 12 human beings actually walked upon between 1969 and 1972, leaving behind small mirrored panels that, more than 50 years later, are still quietly confirming one laser pulse at a time the exact story we've spent tonight telling. It is the same moon that will still be there, gently smaller and gently more distant, for your grandchildren and their grandchildren, and for hundreds of thousands of generations beyond that, steady, reliable, present in the sky on every single one of those nights, in a way that will feel, to every one of those future people, exactly as permanent and unchanging as it feels to you right now. And it is the same moon that in a future so distant, it barely fits into ordinary imagination, will eventually preside over the final chapter of both Earth's story and its own. An ancient, quiet companion, having spent the entire span of its relationship with Earth doing exactly what it has always done, moving patiently, gently, 3.8 centimeters at a time, through a story far larger, far slower, and far more strangely beautiful than anything visible in a single glance upward on any single, ordinary night. Rest now. The moon isn't going anywhere. Not tonight. Not for longer than you or anyone you love could ever need to worry about. It will still be there in the morning, exactly where it has always been, moving at the only pace it has ever known how to move, slowly, patiently, and completely without hurry. Good night. If you're still awake, a few more quiet details. If you're still listening, still drifting somewhere between waking and sleep, here are a few more quiet details about the moon, gathered together gently, with nowhere in particular they need to lead. The far side of the moon, often incorrectly called the dark side, though it receives just as much sunlight across a lunar day as the near side does, was completely unseen by any human being until 1959, when the Soviet Lunar 3 spacecraft captured the first blurry, grainy photographs of it, revealing a landscape strikingly different from the familiar face we see from Earth. The near side of the moon is dominated by large, dark, relatively smooth plains called maria, Latin for seas, though they are not water at all, but ancient, solidified lava flows formed billions of years ago when large impacts cracked the moon's crust deeply enough to allow molten rock from its interior to well up and spread across the surface. Far side, by contrast, has comparatively few of these dark maria, and is instead covered almost entirely by densely cratered, lighter-colored highland terra, a genuine geological mystery that scientists still don't fully understand, with leading explanations involving differences in crustal thickness between the two hemispheres, possibly linked in some models all the way back to the details of the moon's original violent formation. We never see the far side directly from Earth because the moon is tidally locked to us. Its rotation period exactly matches its orbital period, meaning it always keeps the same face turned toward Earth, the same way. As discussed earlier, Earth is very gradually, very slowly locking itself to the moon in return, a process that, as we discussed, is expected to take tens of billions of years to complete, if the sun's own evolution doesn't disrupt the system long before then. More recently, dedicated lunar science missions have continued deepening our understanding of the moon's structure well beyond what the Apollo program achieved. NASA's Lunar Reconnaissance Orbiter, launched in 2009, has mapped the moon's surface in extraordinary detail, including permanently shadowed craters near the lunar poles that may contain significant deposits of water ice, preserved in perpetual darkness and extreme cold for potentially billions of years. A discovery with real practical significance for any future human presence on the moon, since water ice could, in principle, be processed into drinking water, breathable oxygen, and even rocket fuel for a future lunar base or waypoint. NASA's Grail mission, which operated in 2011 and 2012, using twin spacecraft flying in tandem around the moon, mapped the moon's gravitational field with remarkable precision, revealing subtle variations that helped scientists better understand the moon's internal structure, including evidence of ancient volcanic and impact processes buried beneath the visible surface, invisible to ordinary photography, but detectable through their subtle gravitational fingerprint. This growing scientific interest connects directly back to the renewed human exploration efforts discussed earlier. The water ice detected by the Lunar Reconnaissance Orbiter is a significant part of why current lunar exploration plans, including NASA's Artemis program, focus so heavily on the moon's polar regions, rather than the equatorial landing sites Apollo astronauts explored in the 1960s and 1970s. A permanent, sustained human presence on the moon, if it eventually comes to exist, will very likely be built around exactly these ice deposits, tucked away in permanently shadowed craters, waiting in the same patient darkness they've occupied for billions of years, for a use human beings are only now beginning to seriously plan for. There is something fitting in that, as we come to the close of tonight's story. The moon that is slowly, patiently leaving us 3.8 centimeters at a time is also the same moon we are only now beginning to seriously consider living on. Its ancient ice, its ancient far side, its ancient, silent record of Earth's own early violent history, all of it still there, still waiting, still turning the same familiar face toward Earth every single night, for exactly as long as either of us has left to share this particular, quiet corner of the solar system together. Rest now. Truly. Let the story settle. The moon will still be exactly where it has always been when you wake up, and it will still be there, more or less exactly the same, for longer than it is worth staying awake to think about. Good night. On more thing. Supermoons, and the distance that yes, every month. Before we let this story rest completely, it's worth clearing up a detail that often gets tangled together with everything we've discussed tonight, because it involves the moon's distance changing too, just on a completely different timescale, and for a completely different reason. The 3.8 centimeters per year of recession we've spent tonight exploring is a slow, one-directional, permanent drift driven by tidal angular momentum transfer, unfolding across billions of years. But the moon's distance from Earth also changes constantly on a much faster, much more familiar cycle, because the moon's orbit around Earth isn't a perfect circle. It's a gentle ellipse, meaning the moon's actual distance from Earth varies noticeably across each 27.3-day orbit, from the closest point called perigee at roughly 363,000 kilometers out to a farthest point called apogee at roughly 405,000 kilometers. A difference of around 42,000 kilometers, occurring predictably over and over every single month, entirely independent of the slow billion-year recession we've spent tonight describing. When a full moon happens to coincide closely with perigee, the moon's closest approach in its monthly elliptical cycle, the result is what popularly called a supermoon. A full moon appearing modestly larger and brighter than an ordinary full moon, typically around 7% larger in apparent diameter and up to 15% brighter compared to a full moon occurring near apogee, the farthest point in that same monthly cycle. It's a real, measurable, photogenic difference, though modest enough that most casual observers, without a direct side-by-side comparison, would have difficulty distinguishing a supermoon from an ordinary full moon by eye alone. It's worth being clear about the distinction, because the two phenomena are easy to conflate. Supermoons are a fast, predictable, monthly cycle driven by the natural, unchanging ellipticity of the moon's orbit, repeating in essentially the same pattern year after year, century after century, with only the slowest, almost imperceptible influence from the billion-year recession trend gradually, over enormously long timescales, nudging the entire elliptical orbit slightly farther out as well. The 3.8 centimeters per year we've spent tonight discussing operates completely independently of, and at a vastly slower pace than, the monthly perigee to apogee cycle responsible for supermoons. Supermoon tonight is not evidence of anything unusual happening to the moon's long-term trajectory. It's simply the ordinary, predictable rhythm of an elliptical orbit, doing exactly what elliptical orbits have always done, arriving at its closest monthly point at a moment that happens to coincide with a full moon. Looking outward, do other planets have moons like ours? One of the more genuinely exciting frontiers in modern astronomy involves a question this entire documentary has quietly been circling around from the very beginning. Is Earth's particular arrangement a large, stabilizing moon, born from a violent early collision, gently pushing itself outward over billions of years, common elsewhere in the universe, or unusual? The honest, current answer is that we don't fully know yet, though the search is actively underway, detecting moons around planets orbiting other stars, bodies astronomers call exomoons, is extraordinarily difficult with current technology, considerably harder than detecting the exoplanets themselves, because a moon's gravitational and light-blocking signature is so much smaller and more subtle than that of the planet it orbits. As of the time of this documentary, no exomoon has been confirmed with the same level of certainty and consensus thousands of exoplanets now enjoy, though several intriguing candidates have been proposed, most notably a large, Neptune-sized candidate moon detected through subtle variations in the light curve of a planet called Kepler 1625b, first reported in 2018. That particular candidate remains contested within the scientific community, with some follow-up analyses supporting the detection and others questioning it, an appropriately uncertain status for what would be, if confirmed, one of the most significant exomoon discoveries to date. Upcoming and next-generation telescopes, including increasingly refined analysis techniques applied to data from missions like the James Webb Space Telescope, are expected to gradually improve our ability to detect exomoons in the years ahead, potentially transforming this from a field of tentative, contested candidates into one with genuine, eye-confirmed detections, and eventually, perhaps, statistics robust enough to answer the broader question: are large, Earth-Moon-style companion moons a common outcome of rocky planet formation throughout the universe? Or are they a comparatively rare, almost lucky arrangement, specific to the particular, violent circumstances of our own solar system's youth? This question carries real weight beyond simple curiosity, because of everything we discussed earlier about the moon's role in stabilizing Earth's axial tilt, and by extension, Earth's long-term climate stability. If large, stabilizing moons turn out to be rare among rocky, potentially habitable exoplanets, that would suggest worlds capable of maintaining the kind of long-term, stable, moderate seasonal patterns that complex life on Earth has relied upon for hundreds of millions of years, might themselves be comparatively rare, and entirely new, still open for read in the broader scientific conversation about how common or uncommon, truly Earth-like, stably habitable worlds might actually be, scattered across the wider galaxy. For now, all we can say with confidence is this: whatever the final answer turns out to be, Earth's own particular arrangement, this specific moon, this specific distance, this specific slow 3.8 centimeter a year story is, for the moment, still entirely our own. Quiet, patient, ongoing relationship between one planet and one moon, unfolding exactly the way it has for 4.5 billion years, with nothing currently known anywhere else in the universe quite like it. The observatory is still watching, right now, somewhere on Earth tonight. Right now, somewhere on Earth. You listen to this. There is a real chance that one of the handful of observatories equipped for lunar laser ranging is actively firing pulses of light toward the moon, continuing a nightly ritual that has been running, in one form or another, for more than 50 consecutive years. The Apache Point Observatory Lunar Laser Ranging Operation, based in New Mexico, and often referred to by its acronym Apollo, is among the most precise facilities currently conducting this work, capable of measuring the Earth-Moon distance to a precision of about 1 millimeter, an almost unbelievable level of accuracy across a distance of hundreds of thousands of kilometers, achieved by timing the round-trip travel of laser light with atomic clock precision, and carefully accounting for a long list of subtle correction factors. The slight bending of light as it passes through Earth's atmosphere, the precise moment position and orientation of the reflector panels on the moon's surface, even tiny relativistic effects predicted by Einstein's general theory of relativity, which become measurable and significant at this level of precision. Other facilities around the world contribute to this same ongoing effort, including observatories in France, at the Côte d'Azur Observatory, and historically at sites in Hawaii, Texas, and elsewhere, each adding their own nightly measurements to a shared, continuously growing, more than 50-year dataset. Together, these facilities have accumulated what is, by a wide margin, one of the longest and most precise continuous scientific measurement records of any kind in the history of science. A dataset used not only to confirm the moon's slow recession, but also to test fundamental aspects of gravitational physics itself, including precise tests of Einstein's theory of general relativity and searches for any subtle deviations from it that might hint at new, not yet understood physics. There is something worth appreciating in the quiet persistence of this effort. Technicians and astronomers, across 5 decades, night after night, in observatories scattered around the globe, aiming lasers at small mirrored panels left behind by astronauts who walked on the moon before many of those technicians were even born, patiently building, one measurement at a time, one of the most precise and reliable long-term datasets in the history of human science, simply by continuing faithfully to ask the same quiet question over and over. How far away is the moon tonight? Exactly, down to the millimeter. And every single time, for 50 years running, the answer has come back very slightly farther than the night before. A slow walk. Prague. A single night. Acros for de fer and T-Yaras. Let's close gently with one last slow visualization. The same single night, imagined across 4 very different points in Earth's long relationship with its moon. Picture, first, a night 4 billion years ago. Sky above a young, barely cooled Earth is dominated by an enormous, close moon, filling a significant portion of the horizon. Its cratered, dual-forming surface, faintly visible, even without any instrument, lit by a younger, slightly dimmer sun, reflecting off a world with no atmosphere yet capable of producing the soft blue haze we associate with Earth's sky today. Night is short. Earth spins so quickly that this entire scene, sunset to sunrise, unfolds in only a handful of hours. There is no life yet to witness any of it, only rock and heat, and this enormous, silent, newly formed companion, hanging closer overhead than it will ever hang again. Picture. Next, a night 600 million years ago. In the era, the tidal rhythmite rock layers we discussed earlier were quietly forming. The moon is smaller in the sky now than it was in that first, ancient scene, though still noticeably larger and brighter than the moon you know tonight. The day has lengthened to about 21 hours. Ancient forms of multicellular life exist in Earth's oceans, entirely unaware, in any way we would recognize as awareness, of the moon's light falling gently across the water above them, or the tides, driven by that same moon, rhythmically flooding and draining the shallow coastal environments some of that early life may have depended on. Picture now, tonight, this actual, present night, whichever night it happens to be for you, wherever you are. The moon sits 384,000 kilometers away, exactly where it has sat. Give or take a slowly shrinking margin for the entire span of recorded human history. Somewhere on Earth, right now, a laser pulse is very possibly bouncing off a 50-year-old mirror on its surface. Somewhere, a sea turtle hatchling, if it happens to be the right season, is following that same familiar moonlight toward the safety of the ocean. Somewhere, a calendar, older than most of the buildings on Earth, is quietly tracking the same lunar cycle it has tracked for thousands of years. And you, lying here, listening to this, tired, drifting, are simply one more small, temporary presence, sharing this particular, ordinary night with a moon that has outlasted every single night that came before it, and will outlast every night still to come, for longer than there is any reasonable need to keep thinking about it. And picture, finally, a night 1 billion years from now, Dim, by comparison, the moon noticeably smaller in a sky lit by a noticeably brighter, more dangerous sun. Oceans, by this point, are beginning their own long, slow transformation into vapor. Total solar eclipses have already ended, forever, replaced permanently by the thin, ringed light of annular eclipses alone. And still, through all of it, the same fundamental relationship continues, quietly, patiently, exactly as it has since the very beginning. A planet and its moon moving slowly apart, 3.8 centimeters at a time, all the way to whatever ending finally, eventually, awaits them both. How to actually watch this ancient story unfold, Tony, 80 and onward. Even though nothing about the moon's slow recession will ever be visible to the naked eye across a human lifetime, there is still a quiet pleasure in simply watching the moon itself, carefully and regularly, with the knowledge of everything we've discussed tonight sitting gently in the background. The full moon, appearing roughly once every 29.5 days, is the easiest and most familiar phase to observe, rising in the east around sunset and remaining visible through most of the night. But some of the most genuinely striking lunar viewing happens away from full moon, particularly during the first and last quarter phases, when the moon is only half illuminated, and the boundary between its lit and shadowed halves, called the terminator, falls directly across many of its largest, most dramatic craters and mountain ranges, throwing long, sharp shadows that make surface features far more visible through even a modest pair of binoculars or a small telescope than they are under the flatter, more direct lighting of a full moon. Supermoons, as discussed earlier, offer a pleasant, modestly more dramatic viewing opportunity a few times a year. When a full moon coincides closely with the moon's monthly perigee, its closest approach in its elliptical orbit, checking a simple, freely available lunar calendar or astronomy app can tell you exactly when the next supermoon, new moon, or particularly favorable viewing period will occur for your location. For those interested in witnessing, even briefly, a small piece of the deeper story discussed tonight, total lunar eclipses, when Earth passes directly between the Sun and the Moon, casting Earth's own shadow across the lunar surface, and often turning the Moon a deep, striking reddish color, sometimes nicknamed blood moon, remain visible from large portions of Earth's surface several times per decade, offering a rare, direct, visually striking demonstration of the precise geometric alignment between Earth, Moon, and Sun that this entire documentary has been quietly built around. None of this requires any special equipment, any special expertise, or any particular effort beyond occasionally stepping outside, looking up, and remembering, gently, that the pale, familiar object hanging there is not simply decoration in the night sky. It is a genuine, ancient participant in Earth's own history, moving, however slowly, however invisibly, through a relationship with our planet that stretches back over 4 billion years and will continue for billions more, largely indifferent to whether anyone happens to be looking up on any particular night, but no less remarkable for it. Now, we've covered a great deal of ground tonight, or perhaps more accurately, a great deal of distance, 3.8 centimeters at a time, stretched out across 4.5 billion years of shared history between Earth and its moon. We started with a violent collision, a young, molten Earth struck by a Mars-sized world, and the enormous, close, fast-orbiting moon that Callisto Ion left behind. We followed the slow, patient mechanism of tidal friction, transferring angular momentum year after year, gently pushing the moon outward, while gently breaking Earth's own spin, lengthening our days by fractions of a second across centuries. We saw how that same relationship has quietly stabilized Earth's climate, shaped the reproductive rhythms of coral reefs and sea turtles, guided ancient human calendars and navigators, and eventually carried 12 human astronauts across 250,000 miles of space to walk on the moon's surface themselves. We looked forward, across hundreds of millions, and eventually billions of years, toward the quiet, eventual end of total solar eclipses, toward a theoretical state of new dual tidal lock. The Earth-Moon system will likely never actually reach before the sun's own evolution changes everything else first. We looked sideways, briefly, at other moons in the solar system: Phobos, Triton, the Galilean moons of Jupiter, each living out its own version of this same fundamental orbital story, in its own way, on its own timeline. None of it changes anything about tonight. The moon above you right now is exactly where it should be, moving at exactly the pace it has always moved, on a schedule that has nothing to do with you, and asks nothing of you, except perhaps the occasional glance upward and the quiet knowledge now of everything that pale, familiar light has been quietly carrying with it this entire time. Let the story rest now. Let your thoughts rest along with it. The moon isn't going anywhere tonight, or tomorrow night, or for as many nights as you have left to look for it. Good night. A few last numbers, gathered together gently. Before we let this rest completely, here is a slow, quiet gathering of some of the numbers from tonight's story, laid out together simply, the way you might read a list of old, familiar addresses. The moon formed approximately 4.5 billion years ago, out of debris from a collision with a Mars-sized body. It currently sits about 384,000 kilometers from Earth, on average, varying between roughly 363,000 kilometers at its closest monthly approach and 405,000 kilometers at its farthest. It recedes from Earth at a rate of 3.82 centimeters per year, a figure measured continuously since 1969 through lunar laser ranging, using retro reflectors placed by Apollo astronauts and Soviet Lunokhod rovers. Earth's day lengthens by roughly 2 milliseconds per century as a direct consequence of that same recession, a change confirmed independently through ancient eclipse records stretching back over 2,000 years, and through geological tidal rhythmite formations hundreds of millions of years old. Roughly 600 million years ago, Earth's day lasted about 21 hours, with a year of around 400 days. Roughly 4 billion years ago, shortly after the moon's formation, Earth's day may have lasted only 5 to 6 hours. Looking forward, somewhere between 600 million and 1 billion years from now, the moon's continued recession is expected to permanently end total solar eclipses on Earth, leaving only annular, ring of fire eclipses from that point onward. Full mutual tidal lock between Earth and the moon, if nothing else intervened, would take on the order of 50 billion years to complete. A timescale, the sun's own evolution, expected to begin transforming into a red giant in roughly 5 billion years, will almost certainly interrupt long before it is ever reached. Mars's moon Phobos, orbiting only about 6,000 kilometers above the Martian surface, is spiraling inward at roughly 2 meters per century, expected to be torn apart by Mars's tidal forces within 30 to 50 million years. Neptune's moon Triton, orbiting backwards relative to Neptune's rotation, is expected to suffer a similar tidal destruction in roughly 3.5 billion years. 12 human astronauts walked on the moon's surface across 6 Apollo missions between 1969 and 1972, returning nearly 400 kilograms of lunar samples and leaving behind the small mirrored panels still used today, more than 50 years later, to measure the moon's ongoing patient departure, one laser pulse, and 1 millimeter at a time. There is nothing here that needs to be memorized or held onto tightly. These are simply the quiet coordinates of a very old, very slow story. A story that began in fire and collision, that has spent billions of years unfolding at a pace of centimeters. And that will continue long after tonight, long after any of us, at exactly the same unhurried, patient rate it always has. Rest well. The numbers will still be here tomorrow, and the moon, moving at its own unhurried pace, will still be exactly where it has always been. The moon in human memory. There is one last thread worth gently pulling on before we finish. The way the moon has been woven quietly and continuously through human memory itself, across every culture that has ever looked up and wondered about it. Ancient Chinese astronomers recorded lunar and solar eclipses with remarkable precision for thousands of years. Observations later mined by modern scientists to help reconstruct the moon's ancient recession rate. Babylonian astronomers, over 2,000 years ago, developed mathematical methods for predicting eclipses with surprising accuracy, methods that would later influence Greek astronomy and, eventually, the broader development of Western scientific thought. Indigenous cultures across the Pacific, without written records in the traditional sense, passed down extraordinarily detailed oral knowledge of the moon's phase and its relationship to ocean tides and navigation. Knowledge sophisticated enough to guide voyages across thousands of kilometers of open ocean, between islands separated by nothing but water and stars. The moon appears, in some form, in the mythology of nearly every human civilization that has left a historical record, as a goddess, as a god, as a Ra exhibit, as a woman weaving, as a face, as a mirror, as countless other images, each culture finding its own way of making sense of the same pale, patient, ever-changing light. Many of these mythological traditions, independently and without contact between the cultures that produced them, arrived at strikingly similar observations. The moon as something reliable, something cyclical, something connected to water, to tides, to time itself, and to the passage of months. In more recent history, the moon has occupied a strange, singular place as the only celestial body human beings have ever physically visited. The Apollo 11 landing, watched live by an estimated audience of 600 million people worldwide in July 1969. At the time, the largest television audience in human history, remains, for many people who lived through it, one of the defining moments of the entire 20th century. The famous photograph known as Earthrise, taken by Apollo 8 astronaut William Anders in December 1968, showing Earth rising over the moon's barren horizon, is often credited with helping to shift public perception of Earth itself, small, blue, fragile, and alone against the black of space. A perspective some historians argue contributed meaningfully to the environmental movement that gained significant momentum in the years immediately following. All of this, the ancient eclipse records, the oral navigational traditions, the mythology, the live broadcast watched by 600 million people, the photograph that changed how an entire generation thought about their own planet, sits quietly behind and inside the same physical story we've spent tonight tracing scientifically. The moon has never simply been a rock in the sky. It has been, for the entire span of human existence, a shared point of reference, a shared calendar, a shared source of wonder, slowly, almost imperceptibly, drifting 3.8 centimeters farther away with each passing year, while remaining, for every practical human purpose, exactly, comfortingly, reliably the same. The final, true closing. We have reached the actual end of tonight's story now. The last, quiet stretch, gathering together everything that has come before. One final time, slowly, gently, before we let it all rest completely. 4.5 billion years ago, a collision. A world half the size of Earth, striking at a glancing angle, throwing molten debris into orbit, out of which, over a span of time almost too short to believe, the moon assembled itself into a single, close, enormous sphere, hanging low and heavy over a young, rapidly spinning Earth. That first violent moment onward, a single, patient mechanism. The slow transfer of angular momentum, driven by the friction of tides, dragged slightly out of alignment by Earth's own spin, has been quietly, continuously reshaping the relationship between these two worlds. Moon moving outward, Earth's spin slowing down, neither change perceptible within any human lifetime, and yet both changes real, measured, confirmed independently through laser light bounced off 50-year-old mirrors, through ancient eclipse records, inscribed by civilizations thousands of years gone, through layers of sediment laid down hundreds of millions of years before anything resembling a human eye ever existed to look upward at all. Along the way, almost as a quiet side effect of its own gravitational presence, the moon has done something that may matter more to Earth's long habitability than anything else in this entire story. It has held Earth's axial tilt steady, gently resisting the kind of chaotic wandering that appears to have plagued Mars, a planet with no comparably large moon to anchor it. In doing so, the moon may have helped make possible the very thing that allows any of this story to be told or heard at all. A stable, predictable climate, mild seasons, and, ultimately, the conditions in which complex life, and eventually a species capable of building lasers, launching astronauts, and asking questions about its own moon's future, could emerge in the first place. And now, looking forward, that same story continues to unfold at exactly the same unhurried pace it always has. Total solar eclipses, that rare, perfect, coincidental alignment of apparent sizes between sun and moon, will continue for several 100 million years yet, before finally, permanently ending, replaced from that point onward by the thinner light of annular eclipses alone. Earth's day will continue lengthening, fraction of a second by fraction of a second, century after century. And somewhere on the far side of an almost unimaginable stretch of time, long after Earth's oceans have vanished into a runaway greenhouse, not unlike the one that claimed Venus, long after the sun itself has swollen into a red giant, Earth and its moon will finally arrive at whatever ending the physics ultimately assign us them, together, exactly as they have shared every other chapter of this story from its beginning. None of it touches you tonight. None of it needs to. You are here, now, on an ordinary night, under a moon that looks, and will continue to look, for longer than is worth worrying about, exactly the way it has always looked. Pale, familiar, reliable, patient. It has been slowly leaving for 4.5 billion years, and it is, for every meaningful purpose in your own life, and the lives of everyone you love, not going anywhere at all. Let that be enough for tonight. Let your eyes close, if they haven't already. The moon will keep its own quiet schedule, exactly as it always has, needing nothing from you except, perhaps, an occasional glance upward on some ordinary night, sometime in the very long, very patient future still ahead. Sleep well.